what if an element from the periodic table was missing? So what I did was I took my 118-sided die and rolled that, and critically failed that roll, so I rolled a 1. But no, I decided to go with what I assumed to be the most problematic choice, which was hydrogen.
Yeah,
element numero uno.
We each picked our own elements. That's how that worked.
Yep, we each picked our element. I picked hydrogen.
Yeah.
Mostly because I assumed this would break the most things. It turned out it breaks a lot of things.
I would think so.
So, in fact, I'm going all the way back to the Big Bang, because it took me a while to figure out if the universe would even exist. So, Big Bang happens. All the matter in all the universe is compressed into a tiny infinitesimal point, and that thing explodes. And so, for the first fraction of a second, the entire universe is what they call is a group of quark-gluon plasma, which basically is just energy. It is literally a trillion degrees Kelvin at this point in time of the universe. And what is happening is that the very tiny, tiny quarks and things that make up matter are trying to form, except they're being immediately annihilated by the anti-quarks and the anti-gluons and all the antimatter. So that's about like 50-50 matter-antimatter, and they are just annihilating each other. And it actually takes not long, because this is all on the scale of fractions of a second, but until enough energy dissipates, you can't even form the basic building blocks of elements, the neutrons and protons. So after about 3 minutes, the universe is now cooled down from a trillion degrees into a nice toasty 1 billion degrees, which I'll classify, I guess, as universe lukewarm. So this is the first time where elements even have a chance of forming. Actually, not even elements yet, only the nucleuses of the elements, because all the electrons are still in a form of plasma. They're too high energy. They're just zooming around everywhere. They're not connecting to any individual nuclei, which is good because technically, if there's no electrons around it, it's not stable. It's not quite hydrogen. I'm not counting it. So my first problem with hydrogen was that in order to form elements, basically what you have to do is you have to get protons and neutrons to collide together into one big nucleus. And then, you just keep adding protons and neutrons until you get up to whatever element you are. So, carbon is element number 6. It has 6 protons and some number of neutrons. And there'll be variations. It could be carbon 12 or carbon 14, which has different numbers of neutrons. So, the thing is, they don't really combine. You won't get 3 to collide at once. You can only, do 2 together, and then, another 2 together, and then another 2 together. So, you couldn't actually make helium at all, because 2 protons won't go together. So 2 protons just by themselves won't go together. You need at least 1 neutron to kind of cling it together a little bit, because they repel each other. So at the very start of the universe, you can make what they call deuterium, which is 1 proton and 1 neutron that is pushed together. And now what can happen is that this deuterium, which is 1 proton neutron, can now collide with something else, with either another proton to make helium-3, or it can collide with another bit of deuterium to make helium-4, and now you're starting to put together the basic building blocks of elements. It's worth noting that it's actually, so this is 3 minutes after the Big Bang. It's not until 400,000 years later, when the temperature is down to a very cool 4,000 Kelvin, where you can actually start making stable elements. So kind of what happens is, for the most part, is, you'll have these 2 element thing, deuterium form with a proton or neutron, or 2 neutrons, or whatever you want to put together, and they'll basically just immediately get zapped by gamma radiation that's everywhere and explode off into 2 different things again. So it's really actually a low chance of these things forming until you start getting to lower energies where more stable reactions start happening. So after about 400,000 years, our actual universe was made up of about 75% hydrogen, 25% helium, and no other elements. No other elements have formed at this point, because everything else isn't stable enough at the energy levels that they're at, because it's still very hot. So higher elements are unstable at higher temperatures. Heavier elements are unstable at higher temperatures, so they'll break apart into hydrogen and helium. So you don't get anything else besides those 2 for a while. That while being 100 million years. So after 100 million years, the universe has finally cooled down enough that hydrogen and helium, in our case now, since there's no hydrogen being formed, only helium. We only have helium floating around.
It's going to be a lot of helium.
It's going to be a lot of helium.
The universe is going to sound hilarious.
That's the only side effect of having only helium.
Yep.
Yeah, that's it, and everything else is fine.
Real squeaky universe.
We live in a big helium balloon, but no, that's not. We're not quite out of the woods yet. So now, the way the universe goes is after 100 million years, we have all this mass floating around, and now it's finally, just due to gravity, now the mass are slowly starting to coalesce and form the first stars. So the way the stars form is that a bunch of matter comes around, all this helium and hydrogen comes together, attracts itself, and now the force of gravity is pushing it denser and denser and denser into this ball. And as the ball gets pushed together, the center of that ball heats up until it gets to back up to 7 million degrees Kelvin, where now you're starting to get nuclear fusion occurring. And generally the way stars work is that they are fusing elements together to release energy. And the reason that they release energy is that when you actually combine like two hydrogens together to make helium, the mass of the helium is actually slightly less than the two hydrogens by themselves. So you've managed to, destroy that amount of matter or convert that amount of matter into energy. Matter can neither be created nor destroyed. Important point in physics. But yeah, so stars generally run on hydrogen fusion, which I was like, crap, because we just got helium. So stars can't really be going if I'm combining two hydrogens into heliums because I don't have any hydrogens. And so I was doing some more research. Turns out stars do other fusions.
Do. Had to point it out.
This is a science goddamn podcast, Chris.
I have to point it out.
You absolutely
It's a
do not
law
have to
of
point it
nature.
out.
No, it's in the rules.
Yeah.
It's in the rules.
God, come listen to this real smart science podcast. They say do a lot.
Do.
Anyhow, so it turns out, for example, our sun, I'll use that as an example, a fairly typical star, 80% of the reactions that occur in the sun are hydrogen into helium fusion reactions, with 20% of it being actually, I'm going to say helium into helium reactions, which is basically helium-3 with one neutron hitting a helium-4 or like another neutron, and they actually go through a couple combinations where heliums will collide and combine into like going from helium-3 to helium-4, or two helium-3s colliding and making some other stuff. I didn't quite get it because 3 plus 3 made a 3 and a 4, but a 3 and a 4 also made a 3 and a 4, and sometimes 3 and a 4 made a 4 and a 4. So I'm not sure where all the neutrons are going. But there's only so many diagrams of helium that I was willing to look at. But interestingly, so 20% of our sun's reactions are helium, but it actually creates 50% of the energy that our sun emits. So half of it is the hydrogen and half of it is the helium fusion. So theoretically, if it was just helium, I guess our sun would be half as bright. I'm not quite sure if it's just helium how it works, because nobody's answered this question with a real physics degree. But you could still have fusion going on, which is cool, which means we can still have stars that are like our sun. They will last a less amount of time, though. So the hydrogen and helium fusion reactions are what they call the primary phase of the star. And they basically are in here until the helium-3 and the hydrogen numbers are depleted. So once it runs out of that fuel, now it starts becoming a red giant. And so the amount of fusion that they're doing, they're now combining heavier elements. And now it's actually helium and helium are combining to make carbon in the center of the sun. And so it's still a fusion reaction, still emitting energy, but not as much energy as the other force in the sun that are trying to make it expand. So it's the sun starts to expand. And to put into perspective is when our sun hits this point and starts to become a red giant, the outer diameter of the sun will actually reach the Earth. The Earth would be within the diameter of the sun. So red giants get huge. And so the sun's basically taking all this helium, it fuses it into carbon, and now make the core denser and denser and denser. And now carbons will fuse together, and actually goes all the way up to iron. So iron is the highest element that stars will create by fusion. So you go all the way up to an iron core of the sun, element number 26. And at this point, the energy of the fusion reactions are no longer sustainable. Then the star collapses in on itself, creates an incredibly dense core for like a very fraction of a second, and then it explodes. This explosion is actually where all of the rest of the elements come from. So basically, you start off with hydrogen and helium, just in space. They kind of come together into a star. Then that star starts heating up and starts combining them into slightly bigger and bigger elements until it gets up to iron. And then that iron explodes, and that explosion is what creates all the other elements in the universe.
So all this already happens with hydrogen, but without hydrogen, it just happens faster?
I'm not exactly sure if it would happen faster or slower. You could still do fusion reactions with helium. The physics gets a little wonky because it's really just about putting nuclei together. Like the helium is 2 protons and 2 neutrons, or
Right.
Mm-hmm.
And now it's hard to have like you can't have single protons, and like you can't have single protons because that would be hydrogen once it's like in a stable form. So you only have 2s to combine with each other.
Right.
So now that I say that out loud, maybe you don't get odd numbered elements when you're in the star.
It's like getting rid of the penny.
You're getting rid of the penny. You don't need it. It's too small. We don't worry about that element anymore. But basically, the main conclusion is that you could form stars, they could perform fusion, they could explode, so you have a universe that can exist.
Yay.
I like that your point here is stars can still explode, so we're okay.
It's usually the opposite,
Right.
of us being, well, we're not okay.
Usually that's the end point of our question. It's not the start of it.
Yeah, so I took a little bit of a look into what our universe might look like without hydrogen. And so the first thing I was looking at that I remember from high school chemistry is that the elements form compounds based on how many valence electrons they have. So oxygen has 6 out of 8 valence electrons. So it's looking for 2 elements with 2 electrons that it can combine with to make nice stable orbits. It wants to get 2 electrons from somewhere. And a hydrogen has 1 electron going around it, and it wants a second one, so it kind of combines with oxygen. So 2 hydrogens combine with the oxygen to make H2O, which we know is water.
Which is important.
Yeah. So with the periodic table, if you take 1 step downwards, in the same column, all the elements are missing the same number of valence electrons. So typically, they tend to act similar. So right below hydrogen, element number 3 is lithium. And I was like, all right, so lithium should be like fairly close in properties to hydrogen. Like it's missing, it has just 1 extra electron on the outside orbit, and it's just trying to make bonds the same way. It'll combine with the same elements. So I was looking at what lithium 2O was looking at, lithium oxide. And I was trying to see like, okay, so how useful is lithium oxide for us? And so I went on Wikipedia, and according to Wikipedia, lithium oxide is used as a flux in ceramic glasses. It reacts with water and steam, forming lithium hydroxide, and should be isolated from them. So it can be used in ceramic glasses to make colors. It says don't mix it with water and steam, which we don't have to worry about because we have no more water.
That's a plus.
And then lastly, so after that, it just says its usage is also being investigated for non-destructive emission spectroscopy, evaluation, and degradation monitoring within thermal barrier coating systems. It can be added as a co-dopant with yttria and zirconia's ceramic topcoat without a large decrease in expected service life of the coating. And so it's really not super useful. It really doesn't do anything for us anywhere. Lithium oxide has basically none of the properties of water that I'd kind of be hoping to replace things with, where I'd be kind of hoping to just be like, oh yeah, no, it just wouldn't be hydrogen, it would just be lithium, and it would serve the same role. None of that happens, and that's mostly because of what they call hydrogen bonds. And hydrogen bonds are, going back into chemistry, different than covalent bonds. So covalent bonds are typically what you do. It's when the electrons fill in the outer orbits. Hydrogen bonds are different. Basically, the way the hydrogen bond works, hydrogen is super tiny. It's got a low mass, it's got 1 proton, and then the 1 electron. And when it goes by like an oxygen molecule, which is much bigger and has a negative charge, the oxygen kind of sucks up that electron. And they share it, but the oxygen is very greedy and kind of holds onto it closer to the oxygen than the hydrogen. Now, what it causes that is that now the hydrogen nucleus, which is positively charged, is kind of out on its own and has a little bit of a positive charge. And so now that positive charge will unbalance the whole charge of the whole molecule. So if you might know, water is polar, which means one side of a water molecule is positively charged, one side is negatively charged. And the hydrogen bond is the hydrogens kind of lining up and making those connections. So they're weaker than normal bonds, but they do important things like they give water its surface tension. It's the reason why water is such a good insulator. It's the reason water can dissolve things. And because lithium and all the other elements going down from there are heavier than water, heavier than hydrogen, they have another shell of electrons that insulates it, and it won't form like the type of hydrogen bonds. It won't form hydrogen bonds. Not because it's not hydrogen, but because it doesn't work the same way.
It doesn't have that polarity.
Yeah, it doesn't create the polarity because the lower shells of electrons shield that extra positive charge from really making a difference. So basically, you don't have water. You don't have anything like water as we know it. Other important things, DNA is held together by hydrogen bonds. Organic proteins also held together by hydrogen bonds. So really you have none of the organic life that we would know without hydrogen. So yeah, we would have a universe, but we just would definitely not be in it.
It's better than I thought it would be, though. That was a clip from Absurd Hypotheticals, the podcast where we answer dumb hypothetical questions. For the full episode, click on the link in the description.